Hi, it's Nick from Building Point Australia, and welcome to this StatiCa discussion of bracing and eave strut connection details in a portal frame. So I'll move to the connection model that I'll use to illustrate some ways of setting these connection details up, and we can see that we have a number of members and some operations already in place. So the focus today will be on the connection details of the eave strut and roof bracing and also wall bracing angles. Firstly, just to describe, we have 5 members. C is the column, it is the bearing member. We see that indicated there in the title. Also, we see the support. So if there are any unbalanced forces or moments in the connection, then this member supported at this end will do what it can, in a sense, to provide the necessary reactions to create balance or equilibrium in the connection for each load combination. If it's a very weak member, it may be incapable of doing that, and that will show up in the results with excessive plastic strain and perhaps very large deflections. Okay, and we have a rafter, 5-degree pitch, 410 UB54, hot roll sections are grade 300, and the web of this member is 7.6 millimeters thick, and the flange is 10.9. The haunch itself, the way it's set up in StatiCa is as a widener with respect to the web of the rafter, but the shape of the widener can be rectangular or other shape, and we use a triangular with flange. And in this case, we can specify the web thickness. So I've of course used 7.6, the same as the actual section, and the flange is 10.9 thick and 178 millimeters in width. So ordinarily for plates, we would use a plate grade 3678, grade 250, or perhaps 350, or if it's a welded section, 300 or 400. But in this case, because I'm simulating a universal section cut to form a haunch, it is hot roll grade 300 for the haunch elements like this. So this haunch is welded with fillet welds in various areas. 6 millimeter leg fillet there we see on the bottom left when I hover over that item, 8 millimeters there, 10 millimeter leg flange fillet weld to the end plate, and the web of the haunch to the flange is a butt weld to simulate a hot roll section. And the remaining details of the end plate are fairly standard. It's a 25 millimeter thick plate, 200 wide, M20 bolts with standard type dimensions with respect to the section. I guess something quickly to mention before I get on to the bracing connections is the stiffeners through a column in a situation like this. So often we would nominate a stiffener like this and perhaps have it at both locations. So the software would put a stiffener automatically against both flanges. But in this case, I've selected upper only, and therefore it lines up with the top flange. And then I copied that operation, and stiffener 2 is not aligned with a member, but it's aligned with a plate. And then the widener, we see the widener 1B, the bottom left, for that haunch, and therefore that is entered there or picked from the list, or use the pick tool here to select that plate to enter that value there. So this type of method of making sure we use the relative operations to position things as far as possible is highly recommended, because it makes the entry simpler and quicker, and also more adaptable if the rafter size changes here, or even the column size, because we're on a little bit of a slope. The stiffeners will adjust vertically as necessary with this arrangement. Now, moving on to the bracing connection details, let's have a look. I'll firstly create a gusset type connection of the strut to the web of the beam. I want a vertical gusset because I want to attach the leg of the angle to that, the wall bracing. I want to use the same cleat and have that gusset as a common element for both of these members here. And then I want a separate member here. So of course it depends on what you're looking for here. Sometimes end plates are used. We need to consider getting the bracing elements in, particularly the strut. The columns might be sprung apart during erection, and you may well be able to use end plates of a sort, or a short stub member. So entirely up to the designer and perhaps in consultation with the fabricator about some of these practical details. But I'm going to use a vertical plate, as I say. It just depends on the situation if that would be appropriate. But let's see how we go here. So I'll select operation, and there's a range of details that might suit us here, but I've found the connecting plate operation to be the best in this situation. So it looks very similar to the member arrangement. We've got essentially a horizontal member coming in with some bolted plates, an end plate perhaps, a tongue, a gusset, and welded to a column. So that's the sort of thing I want, and let's give that a go. So for the first item in this connecting plate, I need M3, and we could use the pick tool here. Makes it fairly simple. And yes, I want a new plate, and it's related to some other members, and it's picked the column, so that's good. Sometimes it might pick the beam, in which case the weld wouldn't be achieved because the beam has stopped short, of course. And so we've got something slightly like what we would require, but we can see we have a very deep tongue here, and we see that dimension there. I'll knock that back to a smaller dimension, and we could keep on editing these details. For example, we might prefer a circular end plate like this. We can look at these dimensions. Sometimes the transparent view is better for this, and the 325, that seems like quite a large dimension. Perhaps I'd cut that back to something like 200 and start to adjust the width of these different elements here. I won't take the time to go through all of that, except I'd like to just mention that with respect to bolts, we see the transparent view being quite useful for identifying the dimension from the end of the tongue to the bolt here, and we could test this out by entering a 0, for example, and that's right, it's confirmed that arrangement, and I would probably go to something like 35 millimeters here for an M20 bolt, and then perhaps another 70, but I might keep it tight and go to 50 millimeters like this. Now I would need to push this dimension out a bit further, but just sticking with the bolts for a moment, we might go 35 millimeters offset vertically from the center of the circular member. And to reset the position for the next bolt, I'll put a semicolon in and go minus 35, or I might make each of those 40 millimeters, for example. It just depends what I'm looking for. I am conscious of wanting to get a cleat coming from the roof bracing, perhaps sitting in between the bolts. So I'd probably push those details out a little bit more. And I've already set this connecting plate up, so I'll just tick that back on, and we see a more refined set of details here with the 4-bolt pattern that I want. I've got 4 bolts instead of just 2 because I've pushed this out a little bit further from the web of the column than perhaps the minimum would suggest, and that's to allow a little bit simpler erection in between the columns, a bit less springing required, and also I want to create a little bit more clearance for the bolts to the other bracing members and so on. So again, some trade-offs, some details to determine as you're working through the design, of course. In order to create this connection to the wall bracing, I want to make this gusset plate longer. And by the way, we don't have a weld at the moment to the web of the column with that gusset plate. We don't see a solid weld, and in the transparent view we don't see these yellow rectangles indicating the welds that are there in other locations. So that needs to be sorted out. We'll come back to that. And there's a few ways that we could perhaps increase the height of this plate, and let's have a look at increasing this so-called width. It's in the vertical direction, and let's add 100 millimeters top and bottom, so a total of 350 millimeters in height. So a little bit like what we saw before, except for the tongue. So this type of approach might be okay. if I go to the transparent view and look at that direction, the bracing angle is overlapping reasonably well with this gusset on the lower part here, but we have an excess of gusset plate above that location. We could, of course, cut that off. We could introduce a working plane here and cut this plate with respect to the working plane. The working plane is simply an operation like this, and you rotate it or offset it according to the axes as required. Or we could do a plate cut, perhaps referencing the top stiffener, and have no weld and an offset, maybe 150 millimeters down or something like that. So you could try various things to create the correct plate dimension. But I'm going to use the plate editor in this case. And let's have a look at some options here. And if we select this connecting plate operation and select the editor, we see we have a range of possibilities that we might want to edit. And in this case, it would be the gusset. And a handy option here is to select the drawing, maybe make this window a little bit bigger if need be, and then we can roll our mouse and zoom this up and check the end distances and these sorts of details. So it's quite a handy option. And depending on what we're doing, we might be able to put this to the side and use apply if we're setting up other details, see the effect, make some changes, etc. So that's one way to do it. But a simpler way to get to that plate editor is to right click on the actual item, and we don't need to then make a subsequent choice. So it's the same view here as before, and what I want to do is introduce an offset. So the offset now allows us to shrink the size of the plate compared to the original. We can do it on all sides, and in fact if we put a negative value in, we can make the plate grow. So what I want to do is change one of these edges, so edge 4, and I want to use 115 millimeters like that. And here's a case where if we select apply, we see the effect of that change in the window. I can now make further changes if I'm unhappy with it without having to come back into the editor. So just it's a way of doing things a little bit more quickly perhaps at times. And so that's looking a lot better. Again, from this direction, looking at the transparent view, we can compare the overlap that we have and this sort of thing and decide if we have a reasonable detail or plate dimension to work with. All right, now that's fine. Let's see how we go with attaching the angle brace to this existing gusset plate like this. So in terms of the operations, there's a few that might be possibilities. Let's try a fin plate. And of course, the software didn't know what I was thinking and selected the wrong member. So I'll correct that, select that member, and the bottom left, M5 Web 1, yes, we have these details, and it's not connected to the rafter B. I want to connect it to C, and so now it recognizes the correct member and it's welded, but in fact I did not want an extra plate. I wanted to attach it to an existing gusset. So we see with the fin plate that the only option is to create a new plate, and so this is not the option that will work for us in this situation. So I'll delete this and try another operation. Perhaps the connecting plate that we tried before would be worthwhile. So let's try this. It's going to be M5 again, and not a new plate, but an existing plate. And so that's looking a bit more promising. We can select an existing plate, and it's guessed the end plate, so shifted everything across. Let's correct that and go back to CPL1 like this. And so we see a very deep tongue member again that could perhaps be reduced down to something much more sensible, but I don't actually want a tongue anyway. But just in terms of looking at this, let's try the different options. We've got cap plate like that, or cap plate times 2 going each side, or notch plate walls, so the plate is notched. To confirm some of these details, it can be handy to make sure this window is selected, hover over something, and then press delete. So I'll delete from the view the bottom flange of that member, that angle. It's not deleted from the model. If I do something else, it will come back, reset the view. So this confirms that the plate is notched. So some of these options are reasonably similar in terms of the way they look, but you can check what is exactly happening. And this says the member is notched. So let's have a look at deleting that plate, and sure enough, the member is notched this time, not the plate. So, but none of these options suit us. We find that although we can connect to an existing plate with a connecting plate using an angle member, we don't have an option that suits us in terms of the detail there. So again, the connecting plate doesn't work for us here. So I'll delete that last operation. And although we're running low on the range of options, this gusset type connection works quite nicely. So let's use that and correct the member that is being connected. And by default, these operations tend to want to create a new plate, but we can of course select some other details, existing plate, or sometimes it's a member plate, a flange of a column or something like this we could connect our angle directly to. So the flange is, or web of a T-section perhaps, is considered the gusset directly for this sort of connection. So the gusset plate is not valid currently, and let's have a look at some other options that we might use. So we don't need a member plate, we want an existing plate, and we want that to be this gusset here. We want that to be CPL 1A, so here we have it. I see it's welded at the moment, and we want it to be bolted. There is no plate or member adjacent to the gusset plate. Let's have a look at shifting that around a little bit. Perhaps go to the rear like that. Is that working? So we're getting a little bit closer. We see a new bolt that's come in. Hovering over that, we see in the bottom left it's an M16, so let's make that the preferred size that I want to use. And we see it's all getting a little bit cluttered. Also, I'll make a decision at this point to have the angle oriented the other way. So the angles might be back to back in a tension only bracing arrangement. So some might come in on one side, some on another, but on this connection, I want to detail it and check it such that it's going to be coming the other way. Just before I do that, perhaps I'll introduce some offsets here. So for this member, I'm going to bring it down a little bit. So if I turn on the local coordinate system and reset that view, I can see that the local Z is vertically like that. So with this member M5 selected, I'll introduce -40 for the Z, and yes, it moves in the correct direction. So that gives me a little bit more room to arrange the bolts and these sorts of details. And in order to move it to the other side, perhaps let's try some options with gusset 2. I'm going to try aligning it to one of the legs of the angle, and that's looking a little bit better. Try the front, and that seems to be getting a lot better, but something I notice here is that the Z is now horizontal. So because I've attached to the other leg, it's rotated the whole angle. And the problem with that is it could potentially influence the loading. So if you just have axial force, this wouldn't matter. But let's see if we introduce some force just to check this. So I'll enter a new load, and so for M5, I'll put in a downward shear force of 5 kilonewtons like this. And if I go back and make the change that I did before and connected it to the bottom flange to get the correct orientation, we see that the shear force is now horizontal as opposed to vertical, which it perhaps should be. So I don't think this is a good way to change the direction of the angle. So let's just go back and attach this to the web as we had it before, and we see that the force is vertical, the axes are correctly aligned, and an option with the member itself is to mirror it about either axis, and I'll use the mirror Z, mirror about the vertical axis, and happily that has created the correct orientation. The angle leg is pointing the way I want it, and the axes and the force that I entered are in the correct direction. So that's fine. I can untick or delete that. I don't need to work with that anymore to confirm those aspects. Okay, so that's looking a little bit better. Let's think about the position of the bolts here, and we again see that we have some rows and positions, and let's go back to this view, and the 50 millimeters is from the end clearly, and we could work with the other orientation. Now if we go to materials, we could select that angle and scroll right to the bottom and see a dimension here. We don't get a centroidal distance in this view. Of course, we could look up our catalogue for standard sections and so on and work with that value. But this 21.3 millimeters is from the mid thickness of this leg to the centroid. So it's 24.3 millimeters to the full outside of the leg of the angle. So if we enter this value here of minus 24.3 millimeters, transparent from that side, and zoom right in, we see that the bottom leg of the angle does go right through the center of that bolt. So that's one way perhaps if we didn't have a better way. But back in materials, if it's a more complex section, you want to get to the centroidal value, what you could do is enter it in the general cross-section area. So we could enter a general cross-section either when we're on the design tab and editing the member, or in here, welded composed general cross-section, and enter the 90 by 90 by 6 angle. I won't do it again. Here it is. And in this case, we do get the centroidal dimension entered or shown on the screen. So that's one way to get it, but in this case, there's a much simpler way. So let's just go back to that gusset connection and transparent view, and I'll zero this out and use the plus edge. So it's one edge or the other. The other edge is the mid thickness of the other leg. So of course the plus edge is much easier. This is a 90 wide section, and so I need to go minus 45 to get to the center of the angle leg. And we could go to the report, select BOM, Bill of Materials, scroll right to the bottom and see the dimensions of the bolts with respect to the members. It's similar to looking at the plates in the plate editor, I guess, in that sense, but for members as well. So we've got this 50 millimeters distance here. I would probably want to cut that back a little bit, maybe add another bolt like this, and we still have an overlap like this. I could enter the gap between the column and the brace and bump that up a little bit to push that down. And a further detail I might want to enter, instead of pushing it down further, is perhaps we can ask the fabricator just to take the corner off that a bit. And so there's various ways. Again, I'll do a member cut operation on this occasion, and it's going to be member 5 with respect to a plate. Let's pick that plate like this. It's going to be a surface cut with no welding. I don't want it to try to weld. And if we go to the transparent view, we see that it in fact has taken the corner off, and I'll add an offset like that. So the beauty or the benefit of this type of method is that if the angle brace changes in angle or position, or the height of this tongue changes, this type of thing, that the cut distance or the spacing remains the same. And so that's quite a worthwhile option, I think, to do things like that. Also with plates, it doesn't have to be a member. You can cut plates with respect to other plates or members in the same sort of way. So I'm fairly happy with that connection detail now. Perhaps one last thing, let's go back into the editor and review the 2D drawing. Zoom that up with the mouse roller, and we see we've got 35mm edge distance there. I could tweak that one a little bit if need be. And 30mm there. It's an M20 bolt. 1.5 times that is 30. So 30 is an acceptable dimension there. If we want to change that a little bit, of course, that's fine. You could further refine that detail. So that 2D view, I think, is quite handy to just check some of these details via the plate editor. All right. When we come to this final member, we could again look at a range of options. So from the operations, we could think about the gusset plate or the connecting plate, but in this case, I think the fin plate is a good option. We do want a new plate, and so I don't have a problem with that limitation or requirement of the fin plate. I'm going to attach that member, and let's look at which flange. Looking at the bottom left, that's the web 1. This is the bottom flange 1. So yes, M4 bottom flange 1, connect to B. No, that's why there's no weld there. I'm attaching to column, and it's a projection of B that it's trying to attach to, but of course the welds don't work. We need to attach to the column web that's there. And the material of that plate is going to be plate grade 250, and the welds will be 6mm in leg length and on both sides. And I just, before I forget again, I'll correct this weld. I didn't weld the gusset originally because when we later extend it using the editor, the weld doesn't extend at that time. So I don't weld that. I create a weld operation like this, and I nominate the details just as always. So it's going to be this plate is connected to column web with a 6mm leg fillet weld like that on both sides, and there we have it. So that's good. So here we have a fin plate. I've got a little bit of adjustment to do to get that right, but the nice thing about using a fin plate, or another option if a fin plate didn't work, is to use a doubler plate and position it with respect to the bottom flange of that angle, so it's perfectly flush, and then we can cut that plate to the web of the column and also to the gusset that's there. So I'm going to untick that because I've set that detail up previously, fin plate 1 like this, and instead of using gusset 2, I'm going to go back to use gusset 1. My fin plate should be able to cut to that as a plate cut. So there we have it. So the gusset that I turned back on was the same as the one I created from scratch. And this fin plate I've made a little bit wider. So there's various options here. I'm referencing a top of steel. I've added some dimensional increase. So if that 20 was only 0, we see it's flush there. So it's a little bit like the plus edge. We can reference from the top of steel or from the center line. For an angle, it's easy to do from an edge or top of steel, of course, and the spacing of the bolt on the far side is quite large to maintain that distance on the other side. So it's 20mm plus 45, that's the 65 there on both sides. So that just gives me a little bit more width for stability of the main gusset, and also it gives me a reasonable length of weld on both the web of the column and the gusset itself. So the clearances are a little bit tight here. I'm going to move this member up just like before. We can confirm the direction of the local coordinates if we like. So Z is vertical and Y is to the right. And so for that member, I'm going to enter 10 millimeters to the right, just to push it across a little bit, and 22 millimeters up to get that cleat roughly mid-height between the other two bolts. And so I'm fairly happy with that connection now. But one thing to consider, particularly for bracing members with significant axial force and where a non-symmetrical section, in a sense, or not fully symmetrical, such as an angle, is being used, and we're connecting to a leg which is not at the centroid. We've got the tension. The axial force is applied at the centroid of sections in all cases in the software, and similarly with other actions such as shear. And particularly if the shear center is quite distant from the centroid, you want to consider the eccentricity. And of course, for angles, the shear center is at the intersection of the legs. The centroid is a little bit of distance away. So this type of eccentricity can be quite significant in causing excessive lateral bending and plastic strain and deformations and so forth. So we could run this and see how it goes, but with this level of force and this eccentricity, there is too much bending and the analysis would take quite a bit of time. So the recommended approach here is to select one of the other model types to prevent that type of lateral rotation from that eccentricity. And there's a few to choose from. We can go to the support center of StatiCa, look at the effect of these things, but I think an easy way to think of them is to recognize that the remaining terms, N for axial force, Vy and Vz, the shear forces, are still able to be applied to this member, and they are not restrained in those directions. So in this case, the forces can be applied in all directions, but the moments can't be. So this restraint provides moment restraint in all three axes, so including torsion, and but no restraint to forces. And when we look at the load combinations, we see for member 5 now that the loading is grayed out and italic. If there were loads there entered prior to changing the model type, they would still be shown, but they would not actually be applied. In a sense, you could think of them as the loads don't get past the supports that are provided. So the loads that you put in certain sensors won't get into the member. They will be just going to the supports in a sense. As I say, that's perhaps one way to think of it. So this will simulate in a way that the member, the angle, cannot freely rotate about the gusset if it is flexible in a through thickness bending sense, which it will be to a point. So the angle is connected to steelwork at the far end, and there will be a reasonably good resistance to this type of lateral rotation and movement. So this is a reasonable model type, I believe, and simulating the conditions, the situation in the actual structure. So I'll do that also for this member here. So if we use the default model type for a member, so going back to the original default model type for this strut, in the strength analysis, there is no restraint provided to this member. So forces in all directions, moment in about all axes can be applied, and we'll see potentially some rotations. All of these effects will be included in the strength results, looking at deformations and these types of things. But for the buckling analysis for this model type, the situation with respect to restraints is the converse. It is fully restrained. So from both a moment and a lateral point of view, this cross-section that we're looking at is fully restrained. In reality, the restraint is a little bit further away from the node. There is an invisible link called a super element, which has been introduced in the software to allow a little bit more realistic behavior, perhaps some distortion of hollow sections, some warping of eye sections, this sort of thing. But we can effectively consider for the buckling analysis with this model type as this end cross section being fully restrained both laterally and from a moment point of view. So that won't allow a sway buckling mode to show up very easily in the gusset and tongue arrangement. But the other model type, the model type I will use, has a moment restraint in the buckling analysis, but no sway restraint. So there are some implications in terms of the buckling review and the minimum buckling load factor that you need, depending on the model type that you use. And I recommend some articles in the StatiCa Support Center. Simply search for buckling and you can review a number of articles about these issues or these aspects. All right, so at this point, the software is ready to analyze. And instead of using that one, I've got another model right here, exactly the same sort of details and with all of the refinements that you might make just in finalizing some of these dimensional details. Okay, so we can press calculate, or to carry out the buckling analysis as well, we go to the check menu and select stress strain analysis with buckling. And I'll fast forward to the point at which we have results. Okay, so there we are. We see everything passes and we have a minimum buckling load factor of 5.7. So let's have a look at the buckling results. And so we can select buckling shape here and the buckling tab, and we see a range of buckling modes and buckling load factors for each load combination. And in this case, I've got 30 buckling modes run for each load combination, and I could select any row in this table and have a look at the corresponding buckling mode and buckling load factor. It's the lowest buckling load factor that is of course of interest, but we need to look at gussets in particular. So let's have a quick look at this in the software description. So in terms of checking plates, which includes parts of cross sections in the connection vicinity, plastic strain is a key check. The software employs a limit on the extent of plastic strain. So 5% is the default, indicated by the Eurocode, confirmed by validation studies and so on. So in Australia, the material model is assumed to have a linear behavior up to phi times Fy. So at 0.9 times Fy, we start getting yield, then a plastic plateau with a slight slope, and we have a 5% limit on the extent of plastic strain. And the other key aspect in design, of course, when we're using codes, is to consider buckling. We might have local buckling, member buckling, and we need to have a sufficient margin against buckling. And the recommendations from StatiCa that we should have a buckling load factor at least as high as 3 in a connection. So for a web panel that's subject to fairly high shear here, we're getting a shear buckle showing up. For hogging moment compression from the beam into a relatively thin stiffener, we're getting buckling showing up here. So for these sorts of modes, buckling within a connection, I sometimes call it, we ensure that our buckling load factor is at least 3. There's another type of buckle that we need to be particularly mindful of, and that's what we have in this bracing connection. We have a compression member connected via a gusset type of connection to some other member, and in the default arrangement this member can't sway, and so the buckle that we're showing here has been forced to buckle at a half wavelength effectively compared to what it might buckle at if the member could sway. So with an inverse square law, there's a factor of 4 in a sense. We can do some experiments with this in the buckling load factor depending on whether we have sway restraint or not. And so in a sense, this could be considered a compensation, factor of 4 perhaps, this recommended value of 15. So if we do have sway, perhaps we could accept a much lower buckling load factor. But this is something to consider quite carefully. Please go to the IDEA StatiCa Support Centre, search for buckling, and review a number of articles on this point. So if we go back to the connection model, we could consider the buckling modes and look for buckling in the strut here. But at a 10 millimeter thickness, it is very hard to find any sort of buckling problem showing up with this sort of arrangement and loading. So what I did was select a much thinner arrangement for the tongue and the gusset. So instead of the 10 that I started with, I knocked those back to 6 millimeter in thickness. And where we have the default model type, we have a fully restrained situation, and the buckling load factor was about 14.5 there. Now there's a stiffener coming on the other side, so it's not exactly the same as the values I mentioned from the PowerPoint, whether you have just a simple gusset, fully restrained or not. We see a little bit of complication being introduced because of the stiffening effect. But where we do have this fully restrained situation, the buckling load factor is higher compared to the other model type, which I have run the connection for just now, where sway is allowed. We see here in the deformed shape for this buckling mode 8 of load case 2, a buckling load factor of about 10.5, so less than the fully restrained situation where sway was not allowed. Sway is now occurring and it buckles at a lower buckling load factor, but still I think easily high enough compared to about 15 divided by 4, for example, 3.75. So I have no concerns for this connection. These results were for 6 millimeter thickness. I actually have 10 millimeters in thickness for my connection. So at this point, I might select the report and prepare a detailed output, selecting some different options at the bottom right, and complete the design. Thank you very much.